Okay. So in the last couple of lectures, we had been dealing with remote sensing imagery, and especially we have been focusing on how various computer vision models or algorithms can be used in on these remote sensing imagery to establish or to like identify various information from it. Say, for example, like we saw like how to identify built up areas, or how to remove the clouds from the satellite imagery and stuff like that. So today also we will continue to talk on the along the same lines. So we will focus on one particular aspect called multi-source image fusion. So we know that there are different kinds of sources of this remote sensing imagery. That is, there can be different satellites. There are also like this ground-based measurements or sometimes also available. Then there can be measurements from, say, drones, or measurements from aerial radars, and like a whole array of sensing technology is now available to us. So, like they may be focusing on the same region, I mean the same geographical regions, but all of them they use different technology to measure, or for the imaging or sensing purposes. And as a result, like if we try to measure certain physical variables based on them, so we will be we may get different estimates of of that quantity from the different sources. Now, none of them may be individually accurate, but they can reinforce each other. That is, it's possible that none of the measurements we get from, let us say the different measurements are, say, M1, M2, M5, MK, etc. So and there is a ground truth X. Now the observations which we find, like which we are able to get of each, I mean, let us say the actual measurement is X, and we have got M1, M2 up to MK from the different sources. So, but none of them are exactly equal to X. But like we can consider that, like if we, that is, we may be able to get X hat, which is like that is simultaneously close to all of these things. Says by solving a problem like this. And then again, not all of them will have equal weightage, of course, but so, like, let us say like some of the sources may be more reliable than the others, so we can accordingly change the weightage on them. Right. So like one of the earlier approaches for this was to like extract information from the high spatial resolution imagery, and then inject them to the low spatial resolution imagery. So like some of the like some of the sensing devices, they are capable of measuring images which have high resolution, and the others, that is very like more fine grained, and the others may have low resolution, that is they are coarse grained. But then again, the coarse grain images may like they may, it's possible that they have some advantages which the high resolution does not have. So what is done is that, like we measure, like we upscale the upsample the this low resolution image to make it as the same size as the like high resolution image. That is, the number of pixels are like adjusted. But then so this, the low resolution image contains less details than the high resolution image. So even if we increase its resolution by upsampling, so the whatever information is missing will not get them. So we will have to find a way to map them from the whichever high resolution image we have. Or it is possible that we have the high resolution images from one particular region, and we have the low resolution images from another region. So we what we want to create is, we want to create the high resolution images for the second region. So like just upsampling will not solve, because like the low resolution image lacks certain details. So so what we really need is to create something like a mapping from a high resolution image to an upsampled low resolution image, so that those relevant details can be incorporated. So that is one approach. So what we need for this purpose is a mapping function f, which will map from the high resolution image to the upsampled low resolution image. And for this purpose, we can this function f will have to operate on the high resolution image. So for this purpose, we will have to assume certain kind of structures on the high resolution image. I mean, if it is unstructured, then of course, that is the image space will be so large that we will not be able to make any kind of mapping meaningfully. That is, so for that purpose, what is done is that we assume that, or we constrain that these images, they have certain latent structures, and that helps us to fix the, or to estimate this function f. So the different latent structures which people have assumed is the low rank structure or sparsity, or like various other local or non-local structures on these images. Okay. Now, say for example, like in our earlier lectures, at one point we had considered this matrix completion problem, right? That is, we had or the missing data problem. So if for the missing data problem, we had considered the data matrix to be approximately low rank. That means that is, it is some kind of a structure which we had assumed on the matrix. Had we not assumed it, then that is the space of the possible values would be so large that we would not be able to make any prediction meaningfully. But by constraining it with the help of the low rank constraint, then we are able to enforce the constraints. Now, of course, nowadays we have moved away from these approaches, and we now use deep learning. So this deep learning allows us to represent complex transformations from the input images to the target images. So basically, the functions f, which we earlier used to consider, now like we can actually make these functions f arbitrarily complicated by basically representing them with the neural networks, with deep neural networks. So this basically is a task called image to image mapping in computer vision. So like we have seen neural networks which are used for classification or regression and so on. That is, they maybe take a feature vector as input and produce a categorical value label or a real number, something like that, as the output. But in this case, the input is one image and the output is another image. So it's maybe that the input is a high resolution image from one region, and along with it, maybe it is also provided with the low resolution image from another location, and the result might be a high resolution image from the for the second location, right? So this is the task of image to image mapping. Now there is something known as multispectral imaging. So in the last lecture also I was saying that, when we are considering aerial imagery, one kind of imagery is the visible spectrum images. That is such image which where we actually if you look at the image, it will just look at the it will just seem like the Google Earth images, where we see like the roofs of the different buildings. That is, basically we get a top view of the things. But if instead of the visible spectrum, if we do the imaging in other wavelengths which are beyond the visible range, then we can, that way we can get what is known as multispectral images. That is, where images are captured at specific wavelengths across the electromagnetic spectrum. So in the electromagnetic spectrum, only they are visible. There is only one particular range of wavelengths which is called the visible range. But that is, if an image is captured with using one of those wavelengths, then we will be able to make sense of the captured image just by seeing it. But the image may be captured at other wavelengths also which are beyond the visible spectrum. So what I mean the visible part of the spectrum. So now typically what is done in most satellite is that images are captured at multiple wavelengths, not all of which will be in the visible spectrum. So we will get various images which just by naked eye we will not be able to make any sense of. And then one special case of this is hyperspectral images where like hundreds that is there are some hundreds of contiguous spatial bands like this, and they take the images across those wavelengths, so that like we basically we get for the same target region or the target field, we get a number of images across captured across different wavelengths. Now, certain details might be captured in certain wavelengths, and certain and in other wavelengths it may not be captured, and so on. And also the details which we can capture in one wavelength, that is when we capture an image in one particular wavelength which is outside the visible range, that is just by looking at it, it is not easy to map that image to like an image in the visible range. That is an image taken in the visible range will contain, like we will be able to identify various objects like set the tops of buildings, you can see cars, road networks, rivers, say the green cultivated regions, and so on. But if we consider an image from a different part of the spectrum, we may not be able to identify all these things. So now what is needed is that we have got images of the same thing. Let's say I1, I2, I3, and let us say IL. So many different images we have got, like all of them are basically representations of the same thing, let us say X, but each of them is that is the relation between any of these things, any of these images and X is a very complicated one, and it is like it's not something which we know easily, right? So what we can do is we have to use or we have to learn some kind of mapping from the space of these kinds of imagery to the what the things that we are actually trying to measure X. So that is we can learn these kinds of functions F1, F2, F3 up to FL, right? And you that is if we know the ground truth, let us say what we are trying to measure is some particular physical variable. Let us say we have the ground truth, that is the ground based measurements also at every different pixels, so that kind of forms our ground truth. So we basically have to find a way to map each of these images at which are taken at different wavelengths to the like the actual thing which we are, or the actual physical geophysical distribution which we are interested to get. So basically we each of these functions, like they will again of course have their own sets of parameters and so on. So we will have to, what we will usually do is we will represent each of these functions using a neural networks, and these parameters will basically the weights of that neural network. So if we have got sufficient data of both the satellite imagery as well as the ground truth, then we can actually learn to like parameterize all these functions with the help of the neural network. Right. So this way, what we will get is the final goal is that for each pixel in the image, like we will get not only a fixed a particular value, but also a range of uncertainties. That is so each for every pixel, each of these images have captured something. Now again, as I said earlier, these none of these measurements by alone may be able to describe this pixel or this the actual ground truth that this pixel accurately enough. So we need to do some kind of balancing act. That is, we need to do that is some weighted mapping, etc. So all those weights have to be done. But finally, what we need is we need per pixel estimation. So this is called the multiband image fusion problem. That is, we have hyperspectral and multispectral data, and it is framed as an optimization problem by using the handcrafted priors. So optimization problem, what is optimization of what? I mean optimization problem, why? That is because we are basically trying to choose the optimal values of these parameters of the neural networks, of the parameters of the functions, which in turn is represented by a neural network. Now for this purpose, that is, we can also put some kind of priors on these parameters, which might be the sparse or something like that. And when we do the like solve the optimization problem, the way people do the optimization in neural network is of course through something known as like gradient descent and so on, which helps us to identify the optimal values of the different parameters. So now we will consider a few research papers on this particular line. This is the first paper which we are considering. So let us look at the paper first. So this is the paper. So it is a fairly recent one. It appeared in 2018. So in the last Tuesday, we will again go over the abstract and the experiments briefly. So what is happening here? Remote sensing images with different spatial and spectral resolution, such as panchromatic images and multispectral images, can be captured by Earth observing satellites. So normally the pan images, just to show what these pan images is. So here what they are talking about is something called as pan sharpening or sharpening of panchromatic images. So it's a process of merging high resolution panchromatic and lower resolution multispectral imagery to create a single high spectrum color image. So it's like monochromatic. So panchromatic is like the opposite of monochromatic, right? Monochromatic means what? Monochromatic means like a single color. That is at a particular wavelength they have taken the image. Now panchromatic means like they span the entire spectrum, and accordingly they get the high resolution image. Now on the other hand, they can get the low resolution multispectral image, that is at like at multi as I said, like in case of multispectral, we get the images at different that is we can get the or we can get images at multiple wavelengths, but those images may be low resolution. Now on the other hand, there is the panchromatic images, that is like we are not focusing on at a single spectrum. We are considering like we may be considering different parts of the spectrum, but we that for a particular wavelength we are getting a high resolution image. So on one hand we have high resolution image, on the other hand we have like low spectrum but multispectral image. So now we will these different sources of imagery, they are like combined to get a single high resolution color map. Sorry, color image. So Google Maps and nearly every map creating company use this technique to increase their image quality. Now pan sharpening, it produces a high resolution color image from 3, 4 or more low resolution multispectral satellite bands plus a corresponding high resolution panchromatic band. So here this is like this is the high resolution this is a low resolution multispectral image. So you can see there is a collection of images. I mean for a particular region there is a collection of images, and there is apart from that, on other hand, there is a single high resolution panchromatic image. Now what is done is in the that is there is a neural network which transforms both the low resolution multispectral image and the high resolution panchromatic image. Both are in a sense they are reduced to some kind of a an intermediate form, and they are, those are you can consider it as some kind of an encoding. So this part of it's a kind of an encoder network which creates a coded value of this thing, and here this is another encoder network which also creates a coded value of this thing. So we have got so what is done is both the codes, they are merged, they are concatenated to form a like this kind of a we can say an intermediate representation which contains both the information from this part as well as information from that part, and then it is passed through another neural network which basically maps it to the which basically does the decoding part. So we now we have, so here we did the encoding, now after that we do the decoding, and what we get is actually something like the residuals. So what is a residual? Residual is basically what we get if we subtract the target value from the input value. And the input value is something which we have got anyway. Now from the corresponding target value, so let us say the actual values of each of the pixels separately, the difference between what is observed and what is desired at pixel level, that is predicted by this encoding decoding process, and then those residual values, they are added to the input. So input plus residual is equal to output. So finally what we get is the fused result. So like you can see here, it's like a collection of images, it's collection of input images, we get a collection of output images, but these are actually upsampled low resolution image, and this is the upsampled high resolution. I mean not upsampled, these are the high resolution image. Okay. So just to come back to the abstract, normally the pan images possess high spatial resolution but low spectral resolution, while the multispectral images, they have high spectral resolution with low spatial resolution, right? Now, in order to integrate spatial and spectral information content in both the pan and MS images, image fusion techniques are commonly adopted to generate remote sensing images at both high spatial and spectral resolution. High spectral resolution means like there are like in the incoming images, multispectral images, there are it was high spectral resolution, means that we got image at different spec values of or different wavelengths, uh, but at a low spatial resolution, and the panchromatic image that is like at a high spatial resolution. So what we get is like the best of both worlds. That is, we get the estimated pixel values at every high resolution pixel plus for every wavelength. In this study, based on the deep convolutional neural network, a remote sensing image fusion method that can adequately extract spectral and spatial features from the source images is proposed. The major innovation of this study is the proposed fusion method contains two branch network with deeper structure which can capture the salient images of MS and PAN images separately. So so this is what they're showing. So these are the two branches. It's like the multispectral images, they contain some kind of information, some kind of special information, and the panchromatic image that contains some other information. So we train two separate networks where these two things are, I mean the different special information from them are extracted separately. The reason why we have two different kinds of net or two different networks is because the nature of the information or the various features in the two different images will be different. So it's pointless to use the same network. So like build the specialized networks for each of them, which have to be trained, of course, separately. And besides, the residual learning is adopted in our network to thoroughly study the relation between the high and low resolution MS images. So this is what was This is like the residual based. So as you see, the what we have predicted is the residual values, and then the residual values are combined with the low resolution images to get the final result. And the proposed method consists mainly of two procedures. First, the spatial and spectral features are respectively extracted from the MS and PAN images by convolutional layers with different depths. That is what is happening here. Right? You can see that this has depth M, this has depth P. Second, the feature fusion procedures utilizes the extracted features from the former step to yield the fused image. So this is what is happening here. By evaluating the performance on the on some data sets, they show that their this method shows better results than other classical methods. So just coming back to the paper, so let's take a quick look at their data sets. Yes, so like this is a typical example. So this is the, like, as you can understand, this is like a this may be something like a the aerial map of a city, which is like very high resolution, and like you can see the pixel resolution. I mean, at different pixels you have the different values, maybe indicating some the color, so say the green color, etc. Now, if you contrast it with these multispectral images, there are a large number of them, but their spatial resolutions is low. So first of all, it of course has to be up, that is the process of upsampling will create both of them, like will basically bring both of them to the same size, the high resolution as well as the low resolution, and then the fusion of the features will be carried out. So. Yeah, so that coming to the data set, so they have some QuickBird and some Gaussian satellites. The multispectral images and pan images captured by the QuickBird satellite are 2.8 meters and 0.7 meter spatial resolutions. Means like the so these are the multispectral images which are of low resolution. So every pixel is basically a 2.8 meter region, while the in this case, in case of the high resolution images, every pixel is like 0.7 meter resolution. Okay, in case, so this is the in case of one data set, the quick bird, and in the Gaussian data set it is like these numbers are 4 meter and 1 meter. So you can see that in both cases the scaling factor is 4. That is the high resolution images are 4 times that is they have the are 4 times more detailed than the low resolution image. Now, considering the images obtained by different satellites have different characteristics, we prepared two independent training sets for network training. That is, the same neural network will not be used for images from both satellites. Rather, for every source of satellite or for every source of remote sensing imagery, they will build a separate neural network, although with the same architecture. The samples in each set comprises of some 20,000 patches randomly sampled from the corresponding satellite. So these patches is something which we had discussed in the last Tuesday also. That is, for deep learning, we need a very large number of images. Now, we do not, of course, have so many images from the satellite. So what people do is they from whatever images they have, they actually pick up patches of the image and pretend those patches to be actual images. So that way the number of these patch images, these can be quite large, so that these 20,000 patches are randomly sampled, while another 16,000 uh, like so, and a training testing split is carried out. The size of each patch is 33 by 33. So it's a fairly small image, and so like they train the neural network accordingly, specifying both the input as well as the output. So the neural network is trained using the usual approaches. The various parameters are estimated, and then like they are able to do the prediction. So they have shown some result, that is, so here you can see uh, A. So this is like the resampled multispectral image. That is the multispectral image they got at some resolution. Then they actually upsampled it by just replicating the same pixel value, maybe like at neighboring pixels, right? And so it's like this. So it's like yeah. So let us say they have there is a high resolution image which is like these values, which is 4 cross 4 or 5 cross 5, whatever. So they have these values, let us say x1, x2, x3, etc. And then there is a low resolution image which is like just say 2 cross 2. So its values are y1, y2, y3, y4. So now this I want to upsample and make it into a this 4 cross 4 or 5 cross 5 image. So what I will do is I will basically have to keep replicating the values. So I maybe y1, y1, like y1, y1. All these I put y1, then y2, 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 y2. Like so basically I what I am like I have only this much information. So I just keep on repeating them, and like I that way I just through this process of duplication I upsample the low resolution image to a that is to the appropriate level of resolution. But of course these are all dummy values. These are not like the like they will not have like you'll always see that like adjacent pixels having equal values, which is of course not what is desired. Some contrast has to be there. So so yeah, so this is the image you get by just upsampling the low resolution image. So as you can understand, this is quite hazy because of the this duplication thing. And this is the panchromatic image which they have but which is at high resolution. And then like they try and like this is like something like a reference image. So then what they do is they create the multispectral image, or try to create a high resolution version of the multispectral image by passing these two things. This A and B are put as an input to the neural networks. I mean, not only to the neural network which they have proposed, but other alternative architectures also, and they get outputs like this. So like in each case like they have the reference or the ground truth, and they have like what their neural network has produced as output. So they do the like pixel by pixel comparison to check the differences, and accordingly they measure the performance. So this is this is one task. Along similar lines, we have had other papers also in recent years. So let us come to the second paper. So this is talking about multispectral and hyperspectral image fusion by something they have called as MSHS fusion net. So unlike in the previous case, we had multispectral low resolution and panchromatic high resolution. In this case, we have multispectral and hyperspectral image fusion. So let us take a look at what these guys have to say. So hyperspectral imaging can help better understand the characteristics of different materials compared to traditional image systems. However, only high resolution multispectral and low resolution hyperspectral images can generally be captured at video rate in practice. That is, if you are going for multispectral, it can be high resolution, and if you are going for hyperspectral, it can be at low resolution. You cannot do both at high resolution. So this is very similar to the previous problem. That is, we have two sources of data. One is high resolution, the other is low resolution. So in this paper, we propose a model based on deep learning approach for merging the HRMS and LRHS images to generate a high resolution hyperspectral image. Okay, so they basically get the best of both worlds, just like in the previous paper. In specific, we construct a novel MSHS fusion model which takes the observation models of low resolution images and the low rankness knowledge among the spectral mode of the high resolution images in consideration. Right? So, remember the we had earlier mentioned that they make some kind of structural assumption in what they are trying to predict. So in this case, the structural assumption they have made is the low rank, right? Then we design an iterative algorithm to solve the model by exploiting the proximal gradient method. So this is proximal gradient method, some kind of an optimization method. You like just like gradient descent is there. I mean, gradient descent is the basic optimization method, but it had its different variants. So one of them is called the proximal gradient methods. And then by unfolding the designed algorithm, we construct a deep network called the MSHS fusion net with learning the proximal operators and model parameters by CNNs. Okay, and then they have experimental study. So the key contribution here in this paper, so if you look at it, are these two equations. So here it's like saying that there is X is basically the high resolution hyperspectral image which they are interested to get. Let us denote it by X. Okay, so now they are imagining that the observations which they have got, the Y and Z. So Y is the like high resolution multispectral image and Z is the low resolution hyperspectral image. Now they are considering that both of them are transformed versions of the actual of the target image X, but their transformation is done in different ways. So one is by multiplying by a matrix R. This one is obtained by I mean this is obtained by a post multiplying by a matrix R. This is obtained by pre multiplying with a matrix C. Okay, so like you can see that like both are linear transformations but done in two different ways, and then we can but still they are linear transformations, but we in general we can consider a non-linear transformation also. So for that we will just imagine some another function like f1 here and another function like f2 here, and such functions can of course be easily parameterized as a neural network. And then apart from that there are these ny and nz, these are just the noise. Okay. So just to for a graphical view or for a schematic view, so the input, like just like in the previous case, the input is the high resolution multispectral image and the low resolution hyperspectral image. So as you can see in the multispectral image, they have a small, like they have a number of images. They each of them at a different spectra. I mean at a different wavelength. But in the hyperspectral image, you can see that like we have a much larger number of images, each of them I mean that is the images have been captured over a much denser set of these wavelengths compared to in this case, but that has come at a cost, while in this case we could get like very high resolution images. In this case we have to like we could get only low resolution images. So the these both of these things will go as inputs to the neural network to, and the output will be the HRSHS. That is, we will get as many images as the hyperspectral case. That is, for every wavelength we will get an image, but the image will be as high resolution as the multispectral case. Okay, so so basically this is the so there is a CNN kind of thing which will take both sources of input, I mean both sources of images as input, then like learn their various features and find a way to combine the features of the different sources, and then the output is going to be the set of high resolution hyperspectral images. So, so this is so the what the CNN basically does is it is I mean the CNN like it it of course has a layer of convolution and pooling and everything, which you can consider it as something similar to the UNet, right? The like we saw in the last class, UNet, that first there is a set of convolutional layer which reduces the input images to a like a something like a low resolution or a very low dimensional structure, and then there is a decoder part which again upsamples it back to the original place. But there are these skip connections which maintain a parity between the encoded part and the decoded part. So similarly, in this case, what they do is they create a loss function, which they call as the reconstruction loss. So the reconstruction loss basically the compares the images that are produced with the original images at like both at high resolution as well as at low resolution. So that is the images that are being generated, they are going to be at high resolution. So at that same resolution, we have to compare them with the different input high resolution images. But at the same time, because they are being the output is being created at different or a large number of wavelengths, and just like the input, so we have to like we have to downsample the output back to low resolution and then compare it with the low resolution hyperspectral input. So like it is necessary that the whatever is image is being generated, it should be consistent with both sources of the input. So we have two different reconstruction loss. One is the reconstruction loss for the multispectral images, which is at high resolution, and another is the reconstruction loss for the hyperspectral images, which is at low resolution. So that is what they do. They construct different loss functions, and then so they have actually uh, shown the optimization algorithm and so on, and they even have given uh, some bounds about how good an optimization they may be able to get. So basically this is where they have indicated the different those reconstruction loss which we are talking about. And so they have to, so it's an optimization problem, where we have to like minimize those minimize those reconstruction losses. And for this purpose they use the proximal gradient algorithm. So like there are details of this which we need not go into. So finally, like if we go, so in fact, what they do is they build a something like a K stage network. There are K stages implementing K iterations in the iterative optimization algorithm, where the small K stage is denoted as SK. So so it's like instead that is, they have the input image. From the input image they create, they do not jump to the high resolution output right away. They instead they get like let us say an intermediate representation S1. Now that intermediate representation S1 is like from the let us say from the hyperspectral images, that is uh, that is passed on to the next layer, where again it is uh, under like it undergoes a series of operations, uh, like again taking this time taking the multispectral images as as another source of input. And at every stage like the image like after this they get another representation called S2. Now that S2 representation, that is again passed through another round of iterations and to get S3, and this process just continues until for some capital K number of stages, and after which they get the desired image. So that is so they have basically some flow chart kind of thing. So at every stage they get some kind of an image which is like partly in the direction of what they are trying to do. And in each of these stages they have a neural network which basically takes the original image as the input, and that is it's then yes, and then it is incorporated with the high resolution hyperspectral image, sorry, low resolution hyperspectral imagery also at every stage. And then finally, but that is at every stage we keep on slightly improving, that is improving the resolution as well as the spectral size. And then finally we reach the uh, reach the optimal level. I mean optimal resolution. I mean the target resolution as well as the target number of wavelengths. So this guy, for this purpose again they have shown some results. And yeah, so and one more paper along very similar lines is this one. So in this case they have in the first one they had panchromatic image and and multispectral image. In this case they have hyperspectral image and multispectral image. In this case they have RGB image. So to overcome the limitations of existing hyperspectral cameras on spatial or temporal resolutions, fusing a low resolution hyperspectral image or HSI with high resolution RGB or multispectral image into a high resolution HSI has been prevalent. So it's pretty much the same kind of problem which they are solving. Previous methods for this fusion task usually employ handcrafted priors to model the underlying structure of the latent high resolution HSI. So just like in this case, they talked about the low rank approach. So that is, so like you can understand here, that is so they consider this is their model. So now they will be able to solve this, that is they have got y and z, and from that they are trying to estimate x. Now this we will be able to estimate x only if they assume some kind of a prior structure on x. And in this case what they have assumed is that is a constraint on the rank of x. So so what these guys are saying is that in this paper, sorry, yeah, using handcrafted priors to model the underlying structure of the latent high resolution HSI and the effect of camera spectral response of the RGB camera on the super resolution accuracy has rarely been investigated. Uh, so the RGB image which they have got, that has that contains some additional information. So what if that additional information can somehow be passed on to the this low resolution hyperspectral image which they have got? Now, in this paper, we present a simple and efficient convolutional neural network CNN based method for HSI super resolution in an unsupervised way without prior training. Later, we append a CSR, that is camera spectral response optimization layer, onto the HSI super resolution network, either to automatically select the best CSR or to design an optimal CSR under some physical restrictions. So basically what they are trying to say by this is that they have the they have something known as the super resolution model. Now, what is a super resolution model? It's basically that is, it takes a low resolution image and creates a high resolution version of it without what they do is more sophisticated than the crude interpolation or deconvolution kind of approach. So like as I was telling earlier, like you can that is, if you have got a low resolution image, you can always make it high resolution by just repeating or duplicating the values. So that will give you a large but a very blurred image. You will not make much sense of it. Now there are some things which people do to do something better than it. Instead of just doubling the values, maybe they can replace it by the mean of like adjacent values or something like that. So that is these are basically based on interpolation. Again, under interpolation, there are various things like bilinear interpolation, bicubic interpolation, and things like that. Basically, like in what way we are estimating the different pixel values of the larger matrix that we, or the larger image that we are trying to create. So here what they like, that kind of work can also be done by what is known as the super resolution algorithms. So again, there are other deep learning algorithms called sometimes known as SRCNN or deep SD, etc. These are some of the well-known uh, super resolution methods. So what they are saying is that they will use such a super resolution method on the low resolution hyperspectral image, but in doing that they will take guidance from the RGB image. I mean, the RGB image, which is of course the visual in the visual spectrum, that image may contain some additional information which may be absent in the hyperspectral image. So they will convert the hyperspectral images from low resolution to high resolution using these super resolution methods, but in the process they will also incorporate the information from the RGB image. They will use the RGB images as guide for this super resolution process. And specifically from the RGB image, they have something known as a camera spectral response. Now, what that is, it's not relevant to go into the understanding of that. So, like it's like some parameters which they can get from when they are taking as the RGB, or when RGB images are being taken. So that information which is present only in the RGB images, that will be passed on to this super resolution algorithm to make them consistent to whatever, so that whatever hyperspectral imagery are generated by the process are consistent with the RGB images. So for this purpose, so like this model is roughly same as the model which we saw earlier. That is, in the unlike the previous case, we may not have a k-stage model here. So but the main idea remains the same. So this is the main formulation. So there is a high resolution hyperspectral image X. So here you just see that it's represented as B cross Mn. So M and N are the number of rows and columns. That is so we can draw an image like this. So there are M rows and N columns. And then there are, so like we can say that there are B number of channels or B number of bands. Just like in case of normal RGB images, we have three bands, that is R, G, and B. In this case, we can have B number of bands. So the hyperspectral imagery, and this B is for hyperspectral images. This B is a very large number, maybe hundreds or thousands or something. And now this this hyperspectral image X is represented in this way. Now consider a low resolution hyperspectral image HS as like this BMN. So B, the number of bands remains the same because this is also hyperspectral, but this is like smaller MN, small m, small n. So you can say that this is what is actually observed, or this is the images that are actually taken, where these are the target images, the kind of the high resolution images that we are trying to produce. And apart from that, so XL is what we have, X is what we are trying to produce. And apart from that, we also have a high resolution RGB image Y. Its resolution, as you can see, is the same, capital N times capital N, but it's B is, the number of bands B is much smaller. Specifically, B is equal to 3 in this case because it's an RGB image. So one band for R, one for G, and one for B. Now, the input resolution is XL is downsampled version of X in the spatial dimension, and high resolution RGBY can be obtained by downsampling X across the spectra. right? So so as you can see, so this X, the actual, the thing which we are trying to see, this has high number of bands as well as high resolution. So we can say that XL, the hyperspectral images, they have the same number of bands but a low resolution, while Y, the RGB image, this has only three like bands but the same high MN resolution. So we can write both of these XL and Y as some kind of transformation on X, just like we did in the previous paper. And then once again, so these kinds of transformation can be parameterized through a neural network. It's yeah, it's and the neural network. This is what the neural network, the block diagram of the neural network. So they will do the optimization just like they had done in the previous case, and they will in a way to optimize some kind of a reconstruction loss function. So what loss function are to be used here? There, so they have discussed here. So like they have so first of all, they want to maintain the consistency with the RGB guidance. So so from the RGB they were getting like one kind of some information they were getting from the RGB images. So that has to be taken care into the loss function. Similarly, then there are further some special constraints which they have defined, and so those the special so like basically they build something like a loss function to capture all these kinds of effects, and then the parameters of the neural network are chosen in such a way as to minimize these loss functions. And yeah, so that way they get the, so yeah, this is the CSR optimization. So in the abstract they have mentioned that the RGB images, they contain some something known as CSR, and that CSR they have to like pass on from the RGB images uh, to the hyperspectral images that they are trying to create. So how that is done, like they have described here. So we will not go into the details of all these things that may be irrelevant. The main message to be taken across here is that like there are different kinds of images, and they each kind or each different sources of image. Every image is like we can say is incomplete, but it has its own advantages. Like some of them have high resolution, the others but low spectrum, and others may have low resolution and high spectrum or something like that. And now they have to combine the images from all these different sources and create a final representation which is has the best of all worlds. That is, it has high resolution also, it has high I mean spatial resolution also, it has high spectral resolution also, and so on and so forth. Okay. So yeah, so and this is achieved through these kind of neural network, which will take different kinds of images as input, like combine them somehow, and produce the target image as the output. Okay. And yeah, so and for this part, and this is achieved by designing suitable loss functions for the neural network, and the parameters of the neural network are learned in such a way that those specialized loss functions are minimized. Okay. So we'll see some more examples of this that is multi-source image fusion in tomorrow's class. So in the meanwhile, you may have noticed that